Thank you very much for the invitation. Thanks to Thomas in particular for having me and giving me the chance to talk here about the theory of quantum gravity that I formulated 2 years ago and I have been studying ever since, and I think it's very promising. It's based on the idea of fake particle, which is a new quantization prescription that leads to what I claim to be the right theory of quantum gravity. I will explain at the end why I make this claim, but you will understand along the talk that its features are the ones that you certainly are looking for. We will also study some physical implications and predictions. And since the idea behind this is very broad and universal, using a new quantization prescription can be applied in principle to any particle, we will ask ourselves if the existing particles could be this type of new particle, which means a fake particle. Well, there is only one open possibility, and that is the possibility that the Higgs boson is a fakeon. All the other ones can be excluded. So there is an observable difference between being one or the other that can be tested in experiments, and we will see how. We will also discuss the classical limit because, of course, theory of quantum gravity has difficulty in making predictions that can be tested within our lifetime. And in particular, since my entire construction is based on high energy physics, so experiments that are done at CERN, you cannot expect to be able to do experiments at CERN soon for the energies that are involved here. So what about trying to look for non-perturbative systems? We will see that many features survive indeed the classical limit. The classical theory changes also, and that is a good environment where you can study solutions that are not of perturbative nature and maybe look for effects of the new idea. And we will also comment on the Friedman-Robinson-Walker solution, how it is modified. So what is the problem of quantum gravity? The problem of quantum gravity is to make it renormalizable and unitary at the same time. And the renormalizability problem can be easily overcome by means of higher derivatives, which means that instead of having a propagator like this, you have a propagator with a denominator that has a polynomial of higher degree in p squared. That raises a problem because when you decompose that into a sum of propagators that have simple poles, necessarily at least one of them has the wrong sign. So there is a relative minus sign. And so this solves the problem of renormalizability because in the ultraviolet the propagator falls off more rapidly, and 1 over p squared is enough for the theory of quantum gravity that I will talk about. However, the problem of unitarity is that if you use the standard prescription to quantize these poles, at least one of them is unphysical. It is a ghost. Negative probabilities, so on and so forth. But there is a catch. If you use the standard prescription. Let's see. So this brings into the game the key issue here, which is unitarity. Unitarity is the statement that the S matrix should be unitary. And when you write the S matrix as 1 plus it to subtract the trivial part, you get this identity, which is known as optical theorem. Twice the imaginary part of this matrix T is equal to something that is non-negative definite, T dagger T. So the right-hand side has a definite sign, or could be 0, but certainly cannot be negative. And when you write this identity, you can write it diagrammatically. We will see it in a moment. That's very convenient to study it perturbatively. If you insert states from your Fock space W, in and out states, and a completeness relation, forget about this -1 here, plus or -1, you get something like that. So I just inserted the completeness relation in between T dagger and T. That is what you would like, but that is not what you get when you work with higher derivative theories. So to solve the renormalizability problem, you need this kind of propagators, but then when you have those kinds of propagator, you do not get this identity, but you get the identity which I write with this plus or minus here, which means that some states n of your completeness relation will be multiplied by +1, and those are the ones that have a plus mine in front of the residue, and some others, the unphysical ones, are multiplied by -1 if you use the Feynman prescription, which is the plus I epsilon prescription. So this is called pseudo-unitarity equation, and it is what you get in higher derivative theory. The degrees of freedom with -1 are called ghosts, and that would lead to negative probabilities, unphysical, well, things that have problems of interpretation, even from the mathematical point of view, I would say. Can you project those states away just like that? Unfortunately, you cannot, because you can certainly restrict your space of in and out states to a subspace. That's your choice, but you cannot restrict what appears here in the middle. Okay? That's not your choice. Which is what the contraction between T dagger and T. And this comes from the fact that this equation, you see, is quadratic. It's not linear. So there is a contraction of indices here, which is this sum. And you would like to have a completeness relation, at least in the subspace. So if you project away, you ignore the ghosts as in and out states. They reappear as intermediate states in this relation. This is what happens with the usual prescription. Let's analyze it more closely. The optical theorem, as I said, can be written diagrammatically. Diagram by diagram, you have kind of relation like that, which means, for example, this is the simplest relation. Twice the imaginary part of this object is equal to what is called a cut diagram. The cut is the operation that separates T dagger and T, which are built with slightly different Feynman rules, but at the end, it's something non-negative, as it is equal to a cross-section. And the cross-section, this is the integral of on the phase space of the final states. And the cross-section is the cross-section for the process that produces the intermediate particle, which is not virtual here, but real. So when you take the imaginary part, you see, when you take the imaginary part of a diagram, you see what real particles are produced inside the diagram, so to speak. So for example, if you take the imaginary part of the bubble diagram, it's like cutting it like that, and then you have the square of this vertex. And now you have to sum over the phase space of the final states, which are the two states corresponding to the legs in green. These are called cutting equations. More of the story. The optical theorem tells you that certain imaginary parts have definite signs or can be zero, but cannot be negative. How does this fit with the Feynman prescription? This is the Feynman prescription. Well, when you have a propagator, you have a pole like that, and you need a prescription to define it. If you use the Feynman prescription, that's okay, because it obeys the optical theorem. Let's check it in this identity, and the propagator with the Feynman prescription will be here, the green leg. Plus I epsilon gives the sign precisely of the imaginary part. And so if you apply that identity, you will see that the imaginary part of this object, minus I times I, and then there are two i's for the vertices, gives a minus. Then this is plus pi times the delta function on shell, which is also what you get by integrating over the phase space in the other, on the right hand side. This is non-negative, this is okay. So this is the meaning of the Feynman prescription. Can you do something like putting a sign in front of the propagator? No, you cannot, because if you put a sign in front of the propagator, you change the left hand side, but you don't change the right hand side, because the right hand side, you see, is quadratic. And if you change t into minus t, the right hand side doesn't change. So if you change the sign in front of the propagator, you violate the optical theorem, because you will have that the imaginary part of that diagram will be minus pi, the delta. But again, that depends on the prescription. It does not only depend on the residue, it also depends on this, because if I change the sign here also, this thing, for example, would be okay. You change the sign twice, and then the optical theorem is still okay. So the prescription is crucial, and then you can say, okay, I cannot make the usual Feynman propagator coexist with the ghost propagator, but why not making the usual Feynman propagator coexist with this one, where both signs are changed? This cannot be done, unfortunately, because it leads to very bad behaviors. In particular, I've shown with a colleague in Rome, Uguaglietti, who is a physicist from La Sapienza, that in this case you get bad non-local divergences, ultraviolet divergences, even if your theory is local. The theory is mathematically well defined. But there is one way to make the two coexist, in a very particular way, in some sense, which is the fakeon, and now I will tell you about it. So there is a way out to make things meaningful, and an alternative, so to the Feynman prescription. Start from the propagator, 1 over p squared minus m squared, which has poles on the real axis in the p0 complex plane, where p0 is the energy. And normally you know that you circumvent them like that. This is the Feynman prescription. Now, let me put a plus or minus sign in front, because whatever I'm going to say now holds for both signs in front. The sign in front will not be important. It was important with the Feynman prescription, it is not important with the fakeon prescription. And let me multiply and divide by p squared minus m squared. So far I'm doing nothing. Well, at this point, let me introduce an infinitesimal width like that in the denominator. And so I'm splitting those poles there into pairs of poles, and I am distancing them from one another, from each other. The numerator, you can pay no attention to it, because it will not cause any singularity inside the Feynman diagrams. Now you will have 4 poles, and you will have to circumvent them like that, because if you start from here and you double and you split the poles, that's what you get. Observe one very important thing. Once you have poles in the first and third quadrant, and now you do, it's not the same to integrate on the Euclidean or on Minkowski. That's totally different. If you integrate on Minkowski, that's where you generate the non-local divergences I was talking about, and your theory is mathematically not meaningful. But if you integrate like that, which is, you see, like the Wick rotation, you come from the Euclidean and you make the Wick rotation, then you get this kind of particular contour, then it makes sense. And you can check that you have no non-local divergences. Well, the first time that this integral appeared, this integration path appeared, was in the Levesque models, which were studied at the end of the 60s, and Lee and Wick claimed that they were able to give sense to higher derivative theories indeed with this. Skepticism surrounded those models for years, and I began the investigation 2.5 years ago with a PhD student, Marco Piva, who is now in the States, to disprove once for all the Levesque models, because I could not believe that it was possible to make sense of higher derivative theories. And after many attempts, I had to conclude that they were only not defined to the end, not completely understood, but it was possible to solve their problems. Now we will see what problems they lead to and how to solve them, and then this gives a more general idea, which is the fakeon. And in retrospect, you can better understand the Levesque models, which are a particular case of the fakeon. So let's see what happens now in radiative corrections, bubble diagrams, because this identity is fine, It's okay, but you want to see what happens in this and more general identities. So the first diagram you may consider is the bubble diagram. And let's use these kinds of propagators for the virtual particles in between. Okay, the overall sign will not matter. What matters is the structure of denominators. And then to integrate on the loop energy, so the loop momentum is K and the external momentum is P. You separate the integration on the loop energy K0 and you use the Levesque integration path. That tells you how to apply the residue theorem, which poles to consider. You do that and you remain with the integral on the space loop momentum, the space components, of a certain integrand which will be not very complicated. I didn't write it here because it's a little bit long, but you can imagine this is just a rational function. And when you integrate with the residue theorem, you get a rational function with some square roots here and there. These are frequencies. Now, where do you integrate the loop space momentum? You would say R3. Well, this is the wrong part, and this is what Lee and Vic did. But anyway, let's continue with R3 for the moment. You want to know where this amplitude is analytic in the external momentum P. Where is it analytic? When the integrand is nowhere singular. It's when the integral is regular for every k in the entire domain, you're safe. When the integrand is singular in even one k of the domain, you may have problems. And so you work out the location of the singularity. This is also standard because, as usual, the location of the singularity is external energy equal to sum of frequencies, the sum of frequencies of the two virtual particles. And the only difference with respect to the usual story is that here I have these imaginary parts, but otherwise this is what you would get. Okay, this is the location of the singularity, and what is it when you plot it for k in R3? It gives two branch cuts. For k varying on the entire R3, you just get two branch cuts, nothing more than that. But in my case, I have these widths, and because of those, instead of having those two branch cuts, because of these imaginary parts, you have extended regions. And the size of those regions is epsilon. They surround the branch cuts. And that's where the trouble begins, because if you go inside and compute your integral there, you will find, you could complete the computation with the last integral, you will find that you violate both Lorentz invariance and analyticity. Analyticity you might not care, but Lorentz invariance you do care. There is a reason why you violate Lorentz invariance, because if you integrate the loop energy on a funny integration path that contemplates complex energies, because you cannot integrate on Minkowski space, you cannot have Lorentz invariance if you insist to integrate the loop space momentum on real values. You have to deform this integration domain as well, and this is what Lee and Vic missed. So this stopped here. But we went further. This was done with Marco Piva. The first two papers were on Levesque models only. And the answer is as follows. You do need to deform this domain and give complex values to the loop space momenta as well to look for a partner domain of this integration path for the loop energy. And fortunately, it does exist. I can show you, it can be done in any dimension, but in 1+1 dimension it's very explicit. You can even find the explicit, well, in all dimensions it is explicit actually for the bubble diagram. But in 2 dimensions it's easier to describe it. So in 2 dimensions this d3k becomes dk. It's one component, kx. And you complexify kx, and instead of integrating on real values, so instead of integrating on the real line, you check that there is a deformation, a deformed domain like that, D1 I will call, such that the entire extended region shrink to branch cuts, as usual. And so you can say, oh, then it's okay. I know how to compute in these regions. I come from here, for example, from from the Euclidean, and I Vic rotate, and I can reach the real axis from above. That would be the Feynman prescription. That is not the right prescription. Our task is not over yet. Why? Because of this optical theorem that you want to have, because you want to have unitarity, that tells you that the imaginary part is a physical process. And the physical process is the process where the virtual legs become real. So if you have a branch cut, you have a discontinuity, you have an imaginary part, you have a cross-section, you have a production of the virtual particles, but the virtual particles have complex masses. These are the ghosts you want to get rid of. So, okay, with this fine domain domain deformation, you have eliminated these extended regions and shrink them into branch cuts. But again, you cannot compute from above as you would do normally. However, there is a third possibility that is suggested by the very construction. You start from extended regions, right? So there is a third possibility. Don't know if you see it. The third possibility is as follows. You first calculate inside the regions with the wrong domain, which is R3. You violate Lorentz invariance and analyticity, and then you view the result as a function of the domain and deform the domain afterwards. When the domain shrinks, you remain inside. It's like calculating on the cut. And this result has no imaginary part, which means that the unphysical degrees of freedom are not generated by a physical process. And what you get is a fake process. So there is a mathematical theorem that I proved with Piva in the first paper on Levesque models, yes, which tells you that if you do this, you calculate inside and then you shrink, the result is nothing but the arithmetic average of the two analytic continuations you get from above and from below. Okay, so the Feynman prescription would say you calculate from above, and then from below is what you get in the complex conjugate matrix. You remember that you have T and T dagger, two sides of the cut, you see. So in the Feynman prescription, from above is what you get here, from below is what you get there. With the fakeon prescription, instead, you calculate in a different way, and what you get as a result is the arithmetic average of the two.
Excuse me, how do you calculate inside the region?
If you want to...
No, it's a region of singularities.
It's a region of non-analyticity, but the integral is always regular. Actually, it is even continuous. It's always convergent, always regular, but not analytic. It's like having an entire extended region of poles, and you have no analyticity because as soon as you deform the region, some poles float behind your legs, and so you cross. It's like an infinity of contours. This is, for example, the result in the case of the bubble. If you plot it, you will have two analytic functions, one below the threshold and one above the threshold. You will have a continuity, still it is continuous. It's not analytic, but the two functions are both analytic. And so basically, in the case of the bubble, you find this. With the Feynman prescription, you get this famous integral with minus I epsilon in this case. And in the case of the fakeon, you have 1/2 the average of this plus its complex conjugate, which means that you do not have any imaginary part. What are the consequences of this? Well, basically, you have analyticity. This is an analytic function, but it's not related analytically to the other analytic function. in the end you have to split your complex plane into regions, which are disconnected regions of analyticity. And so you have what I call region-wise analyticity. In the usual prescription Feynman, you have analyticity. What does it mean to have analyticity? You can compute your amplitude in any open set of the space of external momenta, one energy here, and then you know it everywhere. Here instead, above those two thresholds, which are the branch cuts, you have different regions, and I can, after I compute on the branch cuts, I can enlarge them into cones using the analytic continuation from there, from inside the branch cut, to make it visually better. But basically what happens is that if you compute in an open set of the Euclidean region, not any region, then you know your amplitude everywhere, but not everywhere by analytic continuation, only in the Euclidean region by analytic continuation. And to overcome these thresholds, you need to use what I call average continuation, which is this operation in which you average two analytic continuations. So this is a non-analytic operation which is non-ambiguous and returns an analytic function. So from here to here you know what to do. From here you cannot go backwards because the analytic average, the average continuation doesn't allow you to. It's an irreversible process. And since this prescription is symmetric with respect to the reflection, with respect to the real axis, the imaginary part vanishes. You can see it here. It vanishes because I have broken the complex plane into different regions. And that is why the imaginary part of the bubble diagram is 0. And that is how now I can, and why I can finally project away those unphysical states. I could not project away them with the Feynman prescription because they were regenerated as imaginary parts. And if I want the optical theorem, as I said, the imaginary parts must be equal to a cross-section. But now the imaginary part must be equal to a cross-section. There was a sum in the completeness relation, if you remember, and it's sufficient to say that your fakeons do not belong to the physical space. So the completeness relation does hold in the subspace. So in this construction there are two ingredients, a new prescription and finally a projection. I stress it very, very carefully and repeatedly because no one has ever found a way to project away consistently states and have consistency with unitarity. The only other projection that is known and is consistent is the one of the gauge theories. Faddeev-Popov ghosts, temporal and longitudinal components of the gauge fields. That is a similar construction where you know that you can project away the Faddeev-Popov ghosts and the longitudinal and temporal components of the gauge fields because of the gauge symmetry. There was no other example of a consistent projection that was not triggered by a symmetry. So somebody asked me, and I said myself asked, is it possible to embed this construction in a symmetry of that type? I don't know. I don't have the answer to that yet. So basically with the standard Feynman prescription you have a pseudo-unitarity equation where you have a plus or minus sign here and not a completeness, a correct completeness relation. Here instead you have, instead of plus or minus 1, you have plus 1 for the physical degrees of freedom or 0 for the unphysical one. 1 or 0. And so once you project away those states in the subspace V, where there are no fakeons, then you have the optical theorem with the right completeness relation. And this you can prove and generalize to all orders. Now, there are some physical consequences of this. And we will describe them now coming to quantum gravity because this is the subject of the talk. Let's see how you can, first, how you can use this in quantum gravity, and then you will see some physical consequences, even in toy models. So even if now I talk about quantum gravity, later I will describe very, very simple toy models with non-relativistic Lagrangians, okay? To describe what happens.
Sorry.
Yes.
Did you have a Lagrangian for this model?
The
The one that generated the loop. So it's some sort of phi cubed.
yes, yes. That the one I was talking about.
Yeah, the one that you.
Yes, yes, yes. That's a sort of scalar model. Yes.
Scalar, but with what sort of kinetic term?
The kinetic term is yes. This is a normal scalar. Okay, so I should have said this. Phi to the fourth, for example.
Mm-hmm.
Take phi to the fourth. You get this propagator. You get the interaction you want,
Yeah.
and then my question is, I can take that scalar and quantize it this way, any scalar. I don't need higher derivatives. That's the point. That's what is beyond Levesque, the Levesque models.
That's just a different prescription.
It's just a different person that you can apply it anywhere. Not really anywhere. We will see in a moment. You cannot really apply it anywhere, but
can you deduce it? Can you deduce this? I mean, you can see that you can modify the prescription that we all learned, but we learned that prescription as a deduction. It's a deduction using Higgs theorem and using all sorts of, from a procedure in which we were trying to compute something very specific. It was, you know, this predefined object that was giving me the scattering matrix. So I started from a prescription to compute the scattering matrix, and then invented the Feynman rules as a realization of these ideas. And if I understand correctly, you are already operating at the level of those rules.
yes,
Can you
exactly.
present what you have done at the level of postulates, new postulates that will lead me to that rules?
I can in one way, yes. Probably it's not the complete answer to what you expect, but for example, one way to obtain the Feynman prescription is the Wick rotation itself. Well, this was one of the starting points to study the Wick rotation, to define higher derivative theories by means of a Wick rotation. And you find that if you use the Wick rotation, you the theory is non-unitary, basically, because you are generating these as ghosts, because you are coming from above in this operation. But there is a non-analytic Wick rotation. So you discover that the Wick rotation is non-analytic, and there is an unambiguous way to, unique to make it, that takes care of new sorts of pinchings that arise when these poles, these quadruplets of poles move around and they touch each other. And so the fakeon prescription is basically associated with a new way of doing the Wick rotation, which is non-ambiguous but not analytic.
I mean, when you.
This is what I can say.
Okay. I mean, the easy, at least I find the easy way to see the Feynman prescription is that you just put a convergent term in the path interval.
Yeah.
Just to make it.
Yes. No, that doesn't work here.
Is there something equivalent here? Or?
I don't think so, because in quantum gravity you don't have that from the start. So you really work perturbatively at the level of Feynman rules, and you use the action as a bookkeeping for the Feynman rules and Feynman diagrams. And then, so your question is, if you want to study this on the lattice, yes, there could be problems with this kind of same problems, or similar, or even more difficult than the problems you find in QCD on the lattice when you want fermions and you want all that kind of stuff that you have in the end.
So I'm confused about your answer to the previous question of Laurent. So the normal phi to the fourth theory doesn't have any problem. So why you say you can apply your method to this? So
because I can.
Okay, but you obtain the same thing as a phi to the fourth.
Absolutely, I obtain, if I apply to the to the phi to the 4 theory, I obtain an S matrix that is identically equal to 1, because the Fock space reduces to the vacuum. There is only one degree of freedom. The scalar is a fakeon. It goes away. I have S equal 1. all amplitudes, all diagrams are real. No imaginary
But at
parts.
some point, your starting point was this relation when you sum over all states, and some of them were give +1 and some other -1. In the fact to the fourth theory, you don't have the -1 to begin
Yes.
with, right?
Yes.
So
I can quantize with the fakeon prescription. I have to quantize with the fakeon prescription all those that give -1. I can quantize with the fakeon prescription even some that have a plus. And this is the issue about the Higgs field. We'll see in a moment. So the best candidate, Lagrangian, the theory is another story because it's not sufficient to give a Lagrangian in quantum field theory. In quantum mechanics, to give a theory, you need to know how to quantize it and to interpret it, and then we will see there are many different ways. For example, this Lagrangian is also the one that leads to the so-called stellar theory, and that is the one where you quantize every degree of freedom with a Feynman prescription, and there you have ghosts. Now we see what to do to define a different theory with the same classical Lagrangian, but we will see in the end that this is not the classical Lagrangian, in my case. So you start from this one because it is local, it is renormalizable, it is unique, it is the only strictly renormalizable you have in 4 dimensions. Zeta, alpha, and psi are just positive constants. I have some redundant constant here, kappa, don't worry, it's convenient. You can add the standard model, you can covariantize it. This is the paper where I formulated this theory. Well, this is a higher derivative theory. And so if you want to go back to the first one of the first slides, it's sufficient to quantize the poles with a positive residue as a la Feynman, or you might want to quantize them as fakeons, and the ones with a negative residue, which are necessarily present because this is a higher derivative theory, those necessarily have to be quantized as fakeons. So this is the idea. And to see it better, it is there is a way to get rid, might know it, or get rid of the higher derivatives and introducing extra fields, then it becomes a little bit more explicit. This theory is, okay, the standard model, fine. The Hilbert term, I set the cosmological constant to 0 for the moment here for simplicity. So this is the Hilbert term. Gravity is described by just the Hilbert term. Then you have a scalar field, the Starobinsky field if you want, which is fine. It has a potential, it has a kinetic term with the right sign. This is positive. But then you have a spin-2 massive field with a complicated action that you can make more explicit, and you will find the action of Pauli fields, which is the action of a massive spin-2. Forget about the non-minimal terms and interactions. So the kinetic part is Pauli fields, but with the wrong sign in front. So this is what normally would be a ghost. In the stellar theory, it is a ghost. But now you know that you can quantize it as a fakeon. And that's it. That's the theory. Phi can be quantized as one or the other, so only an experiment could tell us what is the answer. In the end, gravity is described by a triplet. This is the Graviton Triplet. The fluctuation around flat space is the graviton, a scalar, and a massive spin-2, a massive scalar and a massive spin-2. The masses are ratios of the parameters used in the Lagrangian. So what I want, I inserted this transparency here to tell you about computations we made at one loop, because one of the important features of this theory is that you can compute everything as you can in the standard model. So you can compute loop diagrams, you can resum bubbles. For example, if you resum the graviton bubble, actually the fakeon bubble, you can compute the width of the fakeon, chi mu nu, and this is the result. It's negative. The fakeon, remember this fakeon was the pole with a negative residue. It has a negative width. If you quantize as a fakeon a pole with a positive residue, it will have a positive width. There is a relation. What is the meaning of a negative width? Here we come into one of the prediction of the theory, which is the violation of microcausality. A negative width and other features of the theory that we will analyze in a moment predict that causality is violated at very small distances, and the distances are given by the mass of the fake. 1 over the mass. Energy is larger than the mass, or distances smaller than 1 over the mass. Basically, if you take a bright Wigner and you compute the Fourier transform, not assuming that gamma is positive, just any gamma, you will see that you have the usual damping factor. It's always damping because this is an L2 function, and a Fourier transform of an L2 function cannot explode. And the reason is that you have a theta function in front, but the theta function reverses, switches when gamma is negative. So instead of the past, you see the future.
Is there an implicit violation of Lorentz invariance as well?
No, not at
So
all.
when you say that there is a causality violation at small distances, in which frame should we think of that?
Good question, because this opens a whole new discussion, which is the definition of causality. And we will see, I want to point out that indeed we do not have a clear definition of causality. For the moment, what I mean is as follows. So let me describe it this way. If I use this as a green function, this is, let's say, a propagator for a source, and the response, when gamma is negative, you will find this kind of a response. Forget about the oscillating factor. You have an integral from t to the infinity. So you need to know a source, like the external force of your experimental setup, in the future to predict the present. That's the idea of the violation of microcausality. But how much future do you need? Not much, because there is this damping factor and there is also this oscillating factor actually. And if these masses are very, very small, this fast oscillation dampens the violation quickly. And how large could these masses be? These are free parameters, but even if they are much smaller than the Planck mass, let's say 10 to the 12 GeV, that would mean a violation of microcausality in the realm of the 10 to the minus 36 seconds. So you need to predict the future, what happens in 1 second, you need to guess what happens in between now and 10 to the minus 36 seconds.
But is this expression you write some approximate representation of what is the right thing? Because this seems to violate Lorentz invariance. So
oh yes, this is only the particle is at rest now.
So the thing is Lorentz covariant.
Yes. This is, then you, in the particle at rest, you just use time here to focus on the main point. But I can also show you the formulas for the Lorentz invariant formulas for this. Then you have contribution from the past light cone and contribution from the future light cone, instead of having only contribution for the past light cone. But no contribution from outside the light cone.
So the Stanley term gives rise to the graviton and to this other fakeon field that you introduce. Then you introduce also scalar.
No, the scalar is, I don't know what you call by what you mean by stellar term, but in the Lagrangian,
let's say.
You have these two terms, r mu nu, and r squared. Yeah. Those give two independent fields.
So this gives the graviton and the scalar.
The graviton is here. This gives the fakeon chi mu nu, and this gives the scalar.
The graviton is also present there, right? Because
yeah, but when you do the propagator of this higher derivative theory, you can decompose the poles, and you will see that the graviton pole is the usual one, and then you will have a Pauli fields pole and a scalar pole. And if you introduce them explicitly as independent fields, it's easier to see it.
So if I want to see my loops of quantum gravity start converging at a scale, yeah, maybe it's related to what you said, 1/10 of m Planck.
Yeah.
This means that the mass of that field would be 1/10 of m Planck, roughly.
As long as it's smaller than the Planck mass, like 1/10, the perturbative expansion works. And works up to and above the Planck scale, because it's an expansion in 1 over m Planck. So if the mass of these particles are larger than the Planck mass, then it would be like UCD, like a non-perturbative theory. But so let me remind you that the shortest times we can measure directly is the attosecond is 10 to the minus 18 seconds. What happens below that, who knows if it can be considered time or not. So this theory predicts that something funny happens at 10 to the minus 36 seconds, which is by far included. But the question is, so in the end, you can couple the standard model to this theory with no problem, and that's the only addition you would have. And in principle, you could be able to explain everything with this extra triplet and make the same types of calculations you make for the standard model: perturbative, loop corrections. The renormalization, I didn't say it, is exactly the same as the one of the Euclidean theory, because I forgot to say it, but maybe it is worth to mention. If I make the theory convergent in the Euclidean theory, in the Euclidean regime, once it is convergent, it's convergent. So it doesn't really matter whether I take the continuation from above of or the average of two continuations. If I take the average of two convergent functions, it's convergent because it has been convergent. So since everything is uniquely determined once you compute things in the Euclidean, once you renormalize a theory in the Euclidean, it's fine. It's completely renormalized also here. And so the renormalization coincides with the one of the stellar theory. So a question that you may ask is, okay, since this prescription or new prescription is so general, can you be sure that there is no fakeon among the particles we already know of? And let's see one experiment to make the difference. So first, one observable thing is as follows. Since the fakeon is projected away from the physical spectrum, you will be never able to see it. You will never be able to see it because it's not there. It's only a virtual particle. It mediates interactions, but it cannot become real. But the point is, if you go to CERN and try and check, for example, if you can see Z, W bosons directly, you don't see them either. You don't see the Higgs directly. So that's not the right way to go to see the difference. The difference is in the corrections to cross sections, because the prescription changes imaginary parts. So this changes quantitatively some results. So for example, in LEP you had scattering, the collision between E plus E minus, which produces Z, and that Z decays into E plus E minus. You never see the Z boson, you see its product of decay. And then you plot the results and you will see this peak. That is what you see. You don't see the Z boson, you just see the peak. So could the Z boson, for example, be fake? Since you never saw it, it was virtual, basically.
Sorry, this is not correct, right? So when they discovered the Z boson, they produced it real. What is called technically real, in the sense that I'm not integrating it in a Feynman diagram.
But it's virtual in a tree diagram, but virtual. It's
no, I don't think so. I don't think so. It's on shell. So if you say for the quarks, the quarks are never produced.
You mean
that's
here?
Okay.
Here it's on shell. What is on shell for a particle with a width?
Very interesting philosophical question.
Yeah, but you brought it up, saying that it was on shell.
Okay, so it is a pole on the second sheet.
So do you claim you saw the Z boson directly?
Well, as much as I
probably
see that shell directly, it doesn't get into my head. I just see photos from it.
Describe data with the pole on the second sheet.
Yeah, but maybe you can describe it differently.
Yeah, I think it is a choice of words, this. So what you see is this plot. Okay, this is what you see. This is it. Actually, what you see is this dots here. And the point is that depending on whether Z is fake or not, the plot will change a little bit. And for example, that you see in the corrections, loop corrections first. Not only loop corrections, you need to go to the imaginary parts, because those are the ones that change, and the imaginary parts only contribute above thresholds. So for example, you would like for example, let's consider this, let's see how much, 10 minutes, okay. Let's consider this plot here. You see that starting from this point, you have something like that. This is W plus W minus. It corresponds to this kind of process. But it begins here abruptly, you see, from a threshold which is twice the mass of the W. Exactly twice the mass of the W. That corresponds to the imaginary part. So to the production of W plus W minus. And the threshold is the sum of the cut, the branch cut starts contributing from an energy equal to the sum of the two masses. Now, if the W were a fakeon, the imaginary part would be different, and instead of having this, you would have a slightly different, quantitatively different value. So we can exclude that Z and W's are fakeons simply because those energies have been reached and with the required precision. The point is that Higgs would contribute in this graph, which was missed by Lab 2, a Z boson that generates a Higgs and reabsorbs it, because the threshold for that is above the maximum energy reached by Lab 2. So from that point, you will see an analogous deviation, and you would have two different predictions quantitatively, being H a fake or not. So in principle, this is to tell you that in principle, it's possible to determine whether a particle is a fake or not without even having to observe it directly and getting into difficult questions of interpretation. Now you can say LHC has no problem with energies. And the point of LHC is that it is not equally precise, but I cannot exclude that the answer to my question, is the Higgs boson a fakeon or not, is already buried in the data of LHC, maybe. But it requires a very careful analysis, because you really have to discriminate between the contributions of two imaginary parts, different imaginary parts above the threshold here. So you need a kind of precision that is easier to get in this kind of E plus E minus collisions. So let me skip a little bit of things. So I want to talk about the classical limit, and that's the last comment. Because an important thing is that the starting classical Lagrangian I wrote, the stellar one or the one I rewrote, is not the classical Lagrangian anymore. It's not the classical limit necessarily, because it still contains an unwanted degree of freedom. Something has to be projected away, and it has to be projected away classically as well. So the classical limit is the set of three diagrams, but you restrict the external legs to be the physical ones, so the fakeon is only virtual, and that amounts to integrate it out with the fakeon prescription. Then you get the true classical limit, and now I describe what happens in this classical limit. So the starting action I wrote is called interim classical action. It's local, it's renormalizable, but it is not the true classical action. So you may compare it to a gauge fixed classical action again. A gauge fixed classical action is the one you use, and you use it because it's local. It would be messy to eliminate the gauge degree of freedom by solving the gauge condition. So you use an unprojected classical action, and then in the end you project the unwanted degrees of freedom away. The philosophy is the same, but the technicalities are much different. So basically, to project the classical equation away, you write down all three equations for the 3 degrees of freedom, and you solve the one of the fakeon with the classical limit of the fakeon prescription, and that is, there are no subtlety here about contour integrations, about deformations of domain of integrations, because there is no loop by definition, so it's very simple. It's half the sum of retarded and advanced potentials, and the advanced potentials bring the violation of causality. So let me describe it of microcausality. Oh, by the way, one important thing, since the violation of causality takes place at masses that are larger, at energies that are larger than the mass of the fakeon, you cannot have massless fakeons. Because if you have, you can quantize as a fakeon every massive thing you want, as long as it's very massive, because otherwise you would violate causality, even at low energies or large distances. So you need the thing to be massive. And let me describe what happens with the violation of microcausality. We are studying that in cosmology now with a couple of students, and I think we will produce a paper in a while. I can anticipate that it won't be easy. Actually, we couldn't find any way so far to amplify that violation to have effects at smaller distances. So it's something that apparently stays down there, very well hidden, and in some cases it even arranges itself so as to eliminate itself. But anyway, this is the idea. Take a non-relativistic action, Lagrangian, with an external force, and add a higher derivative term. You get this kind of equation, higher derivative. What is the projection and the fakeon here? The fakeon is this part, and you project it away by inverting it, sending it to the right hand side, and using this prescription, which is the one that comes from the construction I told you. And this is the result. You get an equation like this. Instead of having F equal ma, you have ma equal to an average of the force with an oscillating function, where you pick up the past as well as the future. But since this is very rapidly oscillating, only a very small amount of future will be necessary. But that is, since it's difficult to define causality, and this is how I define it. It's a way, unusual way of writing the equations. And okay, let me skip a little bit of things because I see I have only 3 minutes. As far as quantum field theory is concerned, I would like to point out that the definition of causality is really hard. Actually, there is no definition that is satisfactory. You can check this comment, for example, in Toft and Veltman's diagrammer, where they discuss about the Bogolyubov condition and the Lehmann-Simansky-Zimmermann, which is the condition that fields commute outside the light cone.
Will you show us something like that for the gravity theory, in which I can see that this is not Lorentz violation? Because I mean, this example is nice, but it has that.
Yes, but I only have 2 minutes, so maybe we have to discuss it privately, because I was going into that, but in the case of gravity with Freeman-Robertson-Walker metric.
Here this for time again. So.
I don't see any explicit slide now for that. We will have to discuss it privately. But I want to point out that Bogolyubov's condition, I don't know if you are familiar with it, is as the problem that it's difficult to locate space-time points that are described by relativistic wave packets corresponding to particles that are on shell. So it's difficult to say something is in the future, something comes from the future or to the past. And even the diagrammatic equations that are written in Toft and de Veltman diagram are of shell, and though I doubt if they mean much physically. So my position in this is that losing causality is not a loss at all. But I found very few people willing to defend causality so far, so I didn't have to fight too much in the various communities. I have to add a comment about the other approaches to quantum gravity, a critic to every other approach, of course, because some referee complained that I wasn't mentioning the other approaches in my papers, so I said, okay, I mentioned them, but I criticize them. Well, you know what they are. You have string theory, you have loop quantum gravity, you have holography, you have asymptotic safety. Well, I think that none of them is as close to the standard model as the solution based on the fakeon idea. Because this solution is a quantum theory, it's a perturbative, it admits a perturbative expansion, because you can say asymptotic safety is quantum field theory as well, but it's the assumption that you have an ultraviolet interacting fixed point in the ultraviolet, and so you have necessary to deal with it non-perturbatively. Moreover, it's the assumption on the ultraviolet. You want to assume that the ultraviolet is nice. The ultraviolet, by definition, is the only point we can never reach. So that is my criticism to asymptotic safety. The criticism I have on the others is they are too far away from quantum field theory, and it's something I cannot really understand. Why on earth, after so many successes in quantum field theory, one decides that it's time to throw it away because gravity necessarily cannot be explained within quantum field theory. So it allows to make calculations with an effort that is comparable to the one of the calculations in the standard model. It can be coupled to the standard model, and it can be falsified. With only two new parameters, it could be the most predictive theory ever, because it can cover from the astronomical distances to and beyond the Planck length. So that is the end of my talk. Thank you.
I have a comment and a question. The comment is that the idea that quantum gravity may be just a field theory is, if we want to think fundamental, at the fundamental level and not just at the effective level where I can do some calculations, is very problematic because quantum field theory is predicated on the notion that you have a background space-time structure, and the laws by which you construct quantum field theory presume that you have that you know which points are causally connected and which points are not, and then you construct the whole one. If you don't have that as a given, it's not clear even how to make sense of quantum field theory. But then the second question is the following. When trying to put quantum field theory together with our ideas of covariance, even not concentrating at the moment on how to construct the quantum theory of gravity, one thing we have learned is to deal with quantum field theories in curved spacetime, where a very fundamental lesson is that the notion of particle is at best a secondary notion that can be useful under very special circumstances. And in what you presented, it seems to me that this idea of asymptotic particles, or particles that are real, the particles that are not, the notion of particles seems to be playing a very, very fundamental role, while, as I just said, in quantum field theory in curved spacetime, the notion cannot even be generically defined. How do you address that?
In this theory, one problem, for example, is that in this theory, I have a cosmological constant. And actually, you have a cosmological constant even in low energy effective theory of gravity, because it's turned on by the radiative corrections as soon as you have a massive particle. So you have to deal with that. What is a scattering with a cosmological constant? necessarily you would have to talk about scattering in a non-Minkowski spacetime, non-flat spacetime. There is no theory of scattering that is well formulated in curved space, and there is no no-go theorem that excludes it, but it's not clear what the asymptotic states are, it's not clear what the reduction formulas are, and the S matrix doesn't exist. However, we talk about scattering every day at CERN, and we really do not care whether there is a cosmological constant in the universe. So my approach is very, very pragmatic. I expand around flat space, even if it's not the right one. And around flat space, I have these rules. What is a fakeon, for example, if I expand around a curved space? I would have to resum the expansion around, I would have to reach a curved space from flat space. So that is an entirely open and challenging subject. But for the moment, I have less ambitious goal, which is being able to talk about what we have been talking about so far and more, which is we can make a scattering here, expanding around flat space and predicting cross sections and checking experiments, and this pushes that up to where, and where will everything be consistent and unitary and renormalizable, etc. Up to the moment when the effects of the cosmological constant will become really important, or curvature, or anything that belongs to non-flat, that describes a non-flat space. In the case of a cosmological constant, you would have a detector that is able to detect wavelengths of gravitons that have the size of the universe. That is when you may find a clash. So I do not think I have